So what's the limiting factor behind an energy harvesting design? I guess it's probably the sleep current on whatever host device you're running. What if you could make that sleep current down in the nanoamps? Hey, it's Eamon with ipXchange, and we've got another ipXperience, this one to make up for an interview which went a little wrong at Embedded World. I'm here with William from Nanopower. Before we get started on the technology, William, would you like to just introduce yourself and what you do at Nanopower and what Nanopower does in general?
Yep, sure. Hello, I'm William. I'm CTO at Nanopower. So my role in the company is to develop further the technology to increase power efficiency of systems and overall. We are focused on systems that are battery operated, and we want to decrease the maintenance needs of such systems when they are operating on remote areas or they are on places that are not easy to reach. So our idea is to improve overall efficiency in basically battery operated systems.
Cool. So tell us about the nPZero power saving IC, and there's a bold claim on your website that it can help engineers reduce power consumption by 90%. So yes, what is it and how does it do that?
Yeah, so we call our Gen Zero a smart power management IC. It's smart because it's the only power management with standalone operation features. So our device is able to monitor and manage basically all types of sensors and actuators on the system, avoiding the host to wake up. And we decrease a lot the average power of a system when running on idle mode or reading the sensors and so on. So basically, we consider us a companion, a low power companionship, which is able to fully manage an ecosystem of sensors on a system.
Cool. So in terms of the application areas you see this used in, what are people currently using instead of the nPZero, and why does that not work quite as well as your chip?
Yeah, so people now use what's available on the market. Basically, try to find out low power hosts that operate at low power when the system is waiting for some change on any measurement. But this low power is always on the microamp range, which, if you look at a system that runs 24/7, for instance, on building automation or a body or medical implants or agriculture remote sensors, they are always draining this power. So now with Gen Zero, they are able to run with the same specifications, the same sampling rate, the same quality of data, but running below 3-digit nanoamp. So we operate at 20 nano, and we are
Okay,
fully
wow.
operating in this current range. So this will increase a lot battery lifetime and will decrease a lot the need of maintenance in such sensors where you need to go remotely, or in the case of implants, medical implants, you need to open the body of the person to remove it and do this maintenance. So the
Yeah.
idea is to decrease, or we already have some use cases where the maintenance will never happen till the end of the product. So we already have demonstrators with some type of energy harvesting where we are efficient enough that this harvesting is enough to power up the system, the radio transmission, and the full management of the ecosystem of sensors in such systems.
Okay, so I guess you could call it a power management IC
Yes.
in many regards, but in terms of where it sits in the complete system, how should engineers think about its use and how easy is it to integrate?
Yeah, so we have two types of possibilities. We can operate sitting in between a normal system. We sit in between the host and the sensor. So basically,
Okay.
we have the system itself, the nPZero. It's not only hardware; it's a mix of hardware and an API where the host
Okay.
configures our Gen 0 basically sets rules of how we should operate the sensors. Because when the host sets the rules to our Gen 0, we completely shut down the host. And as we are a master slave architecture, after we shut down the host, we can manage the sensors. So we can power cycle them. We can boot them up, enable power, configure them, read the data, and then compare the data with the rules that were set by the host. If the threshold is above or below certain value, or data between different sensors match some of the rules, we then wake up the host. But this can take years to happen, because if nothing happens or no threshold is met, we are able to run on these few nanoamps, always monitoring the sensors. So we are a perfect fit where you need to have a change to react, and changes sometimes don't happen that often. But we are still always monitoring.
Okay. So in that case, does it also kind of function as a microcontroller as well?
Yes, we we consider our logical blocks, our decision blocks, a subset or a lower brother of a microcontroller, because we cannot code branches or deep decision trees like in C code, but we can do
Okay.
basic logical operations on our state machine, and this is always reconfigurable. We can do some basic logical operations on sensor data. We can do logical operations between different sensors and do some averages on the data and so on. So we can perform some operations, not as many as an ARM or a similar processor core.
Okay.
Yeah.
Okay. So, and at the same time as managing that sensor data, is it also managing the power coming in from energy harvesting and deliverage to the
Yes,
storage
yes,
as well?
yes.
Okay.
One problem we are fixing is that all harvesting technology available, it's able to harvest from a source and put this energy harvested in a container. Consider a battery a container. The
Mm.
problem is when the system needs to wake up. Normally, a host drains so much power. If you measure
Mm.
how much energy was harvested, you will drain this harvested energy before you can use it, because again it's in the
Okay.
microamp range. We
Mm.
can do this check level on still on the nano amp, and we are able to decide if we have a rule that we need to wake up on a 5 minute period, or we need to trigger because some interrupt occurred. We first check if the energy there is enough, so you can send data that's needed to some control system. If it's not, we will wait till it's enough energy, and we will then send the data. I will give you an example.
Yeah. Yeah. Please.
We made some testing on some harvesting setups, where if you need to send each minute some data, and you need 10, the number 10 of energy, you only have 9,
Mm-hmm.
you would never send no data each minute. But if you
Mm.
wait a minute and 10 seconds, you would be able to send data all minute and 10 seconds. So it's better to have delayed information than have no information at all. So we are able to, okay, we don't need the exact timing, but we need the data needs to feel some AI or some platform needs to fill a graph or fill some viewer. So we still
Mm-hmm.
can send data in some timing.
Okay. So in that case, do you think you could build a system around the nPZero alone, or does it always have to have a host and another host?
Yes, we can build a system without a host. We already
Okay.
have some use cases. We are working on implants. We need to monitor
Mm.
something inside the body, and you need to log it. And then at the end of the day, you just need to read the data to see how it was. So we are able to boot from memory. This is
Okay.
not on Gen 0, this version. It will be on the next
Mm.
generation, but we already have
Okay.
a proof of concept how this will work. So basically, in production, we will have a small memory that will hold the recipe or the rules of how we can operate during the 24/7 operation of the device. So we are able to load this data from how we will run, and then we are also able to log the data on this same memory of what happened during this cycle of time. So we can operate hostless, and there are a lot of applications out there which does not need a host. Engineers use a host because till now there was no other option to operate such systems.
Okay, so I guess probably one of your key value propositions is that for ultra low power applications,
Yes.
you've kind of set a new almost kind of made a new device specifically to suit that, rather than having to go through the traditional host architecture. Cool.
Yes.
Okay.
Yes. So we are able to. We saw this need in several systems, and the more we speak with the companies, they are looking at such solutions from years, and we will mitigate this lack of device that is not available now till now.
Cool. Nice. And out of curiosity, in terms of the energy harvesting, what types of harvesters is your device kind of optimized for, or is it pretty open?
Yeah, we are agnostic. Our device is agnostic to anything. It's agnostic to harvesting devices. It's agnostic to radio devices, to MCU. So what we have is we are reconfigurable, and we can reconfigure in runtime. We can adjust, for instance, if the harvesting is able to draw more or less current, we can switch where this current will be flowing. If it's to a super cap, if it's going to charge a battery, if it's going to charge a ceramic cell or a solid state, we can switch where this energy flows. And we also can choose which sensors or groups of sensors are going to be driven by this source. If the battery or this container of energy is not enough to fully run all the sensors and the host, we have a prioritization list where we select, okay, if the energy is that low, but we still need to measure A or B sensor, we will focus on those two and don't read C, D, E, and F. So we are able to route energy when and where it's fully mandatory to put it, to read the sensors there.
Cool. And in terms of, I guess, the amount of sensors you can route, how many would that be?
Yeah,
or how many peripherals can you route at the moment?
Now, in this first generation, we have an I2C interface, which we can drive as many I2C interfaces or sensors that the standard complies. And also we can read or drive SPI sensors. And here we have 4 independent chip selects. So we can have independently 4 SPIs and the amount of I2Cs that the line can hold.
Cool. Okay. And just double checking. So you've been talking about Gen 0,
yes.
And then the next generation. In terms of availability, how available are your chips at the moment? And what kind of production quantities are you going into?
We are now, we had the first batch of full production wafers delivered the initial of this year. We are fixing some issues on testing internally. We found some issues we need to fix. We will be sending out tape out on August, which these fixes will be out at the end of this year, the second full production wafer, and Gen 1 will be taped out next year. We expect will be mid 25, but this all depends on if we could implement all the features we want to have on the second generation of this chip.
Cool. So at Embedded World, you showed me a few different evaluation platforms. So shall we talk about those for a little bit? What do they offer?
Yes, so we built, as I said before, we are fully agnostic to any
Mm.
type of or peripherals or hosts. So what we built here, we built
Hmm.
basically a carrier board which you can plug standard interfaces into it. So our chipset it lies here, and it can manage different form factors. So we built, for instance, an Arduino type, which we can plug any type of Arduino shields in it. So here we have a
Nice.
Nordic. We built another shield with an ST low power chipset without radio. We can plug anything we wish here. And also here on my left side, we have um, uh, interfaces to connect PMOD form
Okay.
factor. So we built when we ship DVD, we have already built some modules we can plug in out of the box, so people can already test our API, interface their hosts with our technology. But of course, as this is a standard PMOD interface, people can, if they have different sensors, of course, we don't have PMODs for all sensors available. People can choose and plug on a different port or whatever their type, their sensor, so they can
Mm.
test. We don't want to bias anyone to use whatever we prefer, because here we don't have preferences. We just want to be. We built a platform so anyone with their ideas, with their technology, what they want to build are fully integratable into our platform. So this will be a plug and play, as you see, a board that you can put anything here, and the core of it is here on our Gen Zero right now. Will be next generation next year, but it will be fully compatible.
Cool. I think that's been a very, very nice introduction to Nanopower, and thank you so much, William,
Okay,
for allowing us to reschedule this one. That was really fun, and we definitely covered a lot more ground than we managed to do at
good.
Embedded World. Cool. Okay, so to everyone watching, that was Nanopower with the nPZero power saving IC. And if you'd like to evaluate this technology, check out the full write up on the ipXchange website and apply to evaluate it today. Thank you, William.
Bye bye.
And hopefully we'll have an update when the next generation comes out.
Yes, of course.
Hey, yo, where my engineers at?